Hello Math 122. In this video I'm going to be talking about section 4.3, which is the third out of 4 sections for chapter 4, and we will be talking about global maximums and global minimums. So we'll begin with a bit of a review from concepts that I talked about in section 4.1. So remember from section 4.1 that a function f has a local minimum at a point P precisely when the value of the function at P is less than or equal to all of the values of f for points that are near P. And f has a local maximum at a point P if the value of the function at P is greater than or equal to the values of f for points that are near P. So notice that in both of these definitions, the term local that is showing up here is meant to represent the fact that we're only comparing the value of the function at P with the value of the function at points that are near P, so in a small neighborhood around that point P. But we can change this definition a little bit to talk about what are called global extrema, or global minimums and global maximums. So again, let f be some function, then f has a global minimum at a point P if f of P is less than or equal to all of the values of f. So this time we're not just looking at a little neighborhood around that point P, but instead we're looking at all of the points in the entire domain of the function f, and we're forcing the value at the point P to be less than all of the other values. And f has a global maximum at P if f of P is greater than or equal to, again, all of the values of f. So not just around a small neighborhood at x equals P. So some examples of what I'm referring to here. In the function on the left, we're specifying that the domain of this function is not going to be all of the real numbers. So we're only looking at the x values between negative 1.5 and x equals 1.5. And we want to find the global maximum and the global minimum. So the global maximum is the point and the value such that no other value of the function is bigger than that value on this domain. And that global maximum is occurring all the way on the right side of the interval. So that purple point labeled global maximum, you can see that the value of that point is bigger than the value of all of the other points in the domain. And the global minimum is on the left-hand side of the interval in this case, and the value of that point is less than or equal to the value of all of the other points inside of this domain. So in this first example on the left, the domain contains the endpoints, negative 1.5 and 1.5. And in the case that our domain contains endpoints, we are guaranteed to have a global maximum and a global minimum as long as our function is continuous. In the other example on the right, we're looking at x values over the entire real line. So our function goes as far as we want to the left, it goes as far as we want to the right. And in this case, we're not guaranteed to have a global maximum or a global minimum. We could have neither, we could have one, or we could have both of them. In this case, we don't have a global minimum because my function decreases as far as I would ever want it to the left and to the right. But we do have a global maximum, and that global maximum is occurring at x equals 0 because the value of the function at that point is bigger than the value of the function at any other point. So, just like with our local extrema, we have methods for finding the global extrema, but these methods are going to be a little bit different depending on whether our domain of the function contains its endpoints or doesn't contain its endpoints. So we'll start with the easier case, when the domain of the function does contain its endpoints, and in this case we would say that the domain of the function is closed. So if the domain of the function is closed, and our function is continuous, so this is important as well, we can do the following to find all of the global maximum and the global minimum. So we start off by finding all of the critical points of the function f inside of the domain. After that, we calculate the value of all of those points that we found in the first step, so all of the critical points, as well as the value of the function at the endpoints of our interval. And finally, using that previous step, we're going to take the greatest value, and that's going to be the global maximum of the function, and the least value from that previous step is going to be the global minimum of the function. So we find the critical points, evaluate the function at the critical points and the endpoints of our interval, and then the biggest of those values is the global maximum, and the smallest of those values is the global minimum. When the domain is not closed, our task becomes a little bit more difficult. So this time, assume that our function is continuous on some interval, but that interval is not going to include endpoints, or the interval can be the entire real line. So in this case, again, we start by finding all of the critical points of the function f in the domain. We then sketch a graph of f. So this is a little bit different than the previous test. And finally, we look at that graph and determine from it where the global minimum is going to occur and where the global maximum is going to occur if they exist. Because remember, when the domain is not closed, those two things, global minimum and global maximum, do not necessarily exist. So you might be asking, well, if I'm going to sketch a graph anyways, why not just sketch the graph from the beginning, ignore the critical points, and just read where the global maximum is and where the global minimum is? And the reason is a little bit subtle, but maybe I'll talk about it later when we get to our example involving a domain that's not closed. So the first example is going to use a domain that is closed. And here we're looking at the function f of x equals x cubed minus 9x squared minus 48x plus 52. So this is a function that we've seen before. And we're specifying that we're only looking at x values between -5 and 14. And our interval here contains the endpoints. So the domain is closed. So we start by finding the first derivative in the hopes to find our critical points. And we take the first derivative and get 3x squared minus 18x minus 48. So if you want to see why this is true, I encourage you to just pause the video and check it for yourself. We take the derivative and set it equal to 0 to find our critical points. So we have 3x squared minus 18x minus 48 is equal to 0. And after factoring, we get 3 times x minus 8 times x plus 2 is equal to 0. And we can conclude that the only critical points occur at x equals 8 and x equals -2. So after this, because we're working over a domain that's closed, we're going to take all of the critical points that we just found, and we're going to take the endpoints of our interval. So in this case, that's x equals -5 and x equals 14. And we're going to plug all of those x values into the function f, and we're going to see what values pop out. So if we plug in 8, we get -396. If we plug in -2, we get 104. If we plug in -5, we get -58. And if we plug in 14, we get 360. Finally, this is enough information for us to determine what the global maximum is and what the global minimum is. So we take the largest output value from the previous step, which in this case is 360, and that's going to be the global maximum of our function. And that global maximum is going to occur at x equals 14. On the other hand, if we look at the smallest value that occurs, which is -396, this is going to be our global minimum. So our global minimum is -396, and that global minimum occurs at the x value 8. Okay, now for an example where the domain does not include endpoints. So a little bit different here. In this case, we're looking at f of x equals 1/4 x to the 4th plus 5/3 x cubed plus 3x squared, and we want to find the global maximum and minimum, if they exist in this case, on the entire real line. So this time, the domain of our function does not include endpoints, so our solution will be a little bit different. Again, we start by finding the first derivative so that eventually we can get our critical points, and the first derivative is x cubed plus 5x squared plus 6x. Again, if you want to see why that's the case, pause the video and work it out for yourself. We set the first derivative equal to 0 to find our critical points. So x cubed plus 5x squared plus 6x equals 0. And now we can factor, and we get x times x plus 2 times x plus 3 is equal to 0. So we can conclude that we have 3 different critical points for our function. And those critical points are occurring at x equals 0, x equals -2, and x equals -3. Now we move on to the second part. So again, remember we just found that we have critical points at x equals 0, x equals -2, and x equals -3. The next thing to do is sketch a graph of our function f. So I took that function f, I put it into Desmos, and this is what popped out. So you can notice we have our three different critical points at x equals -3, x equals 2, and x equals 0 over here. And you can read off of the graph here that the global minimum is going to occur at that critical point at x equals 0, and there is no global maximum in this case. So here is the importance of finding the critical points before we graph. So because we found all of the critical points, the function must continue to increase to the left of that point at x equals -3 and to the right of x equals 0. So why is this the case? Well, if I went off to the left of x equals -3 and say somewhere over here, my function started decreasing like this, so that eventually I got all the way past what I thought was the global minimum, which is occurring at x equals 0. Well, for that to happen, there would have had to be another critical point somewhere up here. But I found all of the critical points, so I know that my function can't decrease to the left of x equals -3. And I also know that my function can't decrease somewhere over here to the left of x equals 0. So the reason I'm finding the critical points is because it tells me about the behavior of the function to the left and to the right of all of my critical points. So I know that there can't be a point somewhere outside of my view here where the function eventually comes down here and gets smaller than the function at x equals 0. So we can conclude that there's no global maximum, but there is a global minimum, and that global minimum occurs at x equals 0, and the global minimum is just 0, because if we take x equals 0 and plug it into the function, we get 0 to pop out. Okay, here's our last example for this video, and it's an important application of these global maximums and global minimums, and these applications will show up in your homework, so this is why I wanted to show it to you. All right, so in the example, we're given that the perimeter of a rectangle is 64 centimeters, and our goal is to find the length of the sides of the rectangle that give the maximum area. So we have this restriction on the rectangle here, that the rectangle has to have a perimeter of 64 centimeters, but we're allowed to change the width and the length of the rectangle, and we want to do it so that we get the maximum area possible. So let's use these ideas that we've been talking about to find a solution. So we're going to let the letter L denote the length of our rectangle and let W denote the width of our rectangle. And we're going to denote the perimeter of the rectangle by P and the area of the rectangle by A. So just some basic geometric formulas. We have the formulas for our rectangle here. The perimeter is equal to 2 times the length plus 2 times the width. And the area is equal to the length of the rectangle times the width of the rectangle. But we're told at the beginning of the problem that the perimeter of the rectangle has to be 64 centimeters. So we have 64 is equal to 2 times the length plus 2 times the width. And we can use that equation to solve for the width in terms of the length. So if we do that, we find that the width is going to be equal to 32 minus the length of the rectangle. So we can take this expression, W equals 32 minus L, and plug it into our equation for the area, and we find that the area of the rectangle is going to be equal to -L squared plus 32L. And so if we want to maximize the area of the rectangle, it's equivalent to maximizing this function A. So saying this in another way, if I let A be the function f of L, so that f of L equals -L squared plus 32L, to maximize the area, it's equivalent to maximizing this function f of L. And so at this point, I've reduced this problem to a problem about global maximums that we've already talked about. So let's see if we can find the global maximum of this function f of L. Okay, so just as a reminder from the last slide, we found that we have this function f of L equals -L squared plus 32L, and this function gives us the area of the rectangle. So to maximize it, we start out by finding the critical points. So we take the derivative of the function f, and we get -2L plus 32, and we set it equal to 0, and find that L has to be 16. So the only critical point that we have is occurring when the length of the rectangle is 16. From here, we can sketch a graph of the function f, and we're sketching a graph here because the domain of my function f can be anything here. I don't necessarily know that the domain is going to be closed, although you might be able to present an argument for why the length has to be between 0 and maybe 64 or something like that. But in this case, it's easier just to assume that the domain can be anything. So I can put in any value for L and it would be fine. So I sketch a graph of the function f of L, and when I look at the graph, I see that the global maximum is occurring right there, and that ends up being L equals 16. So the global maximum of our function is occurring at L equals 16, and we can conclude that the rectangle of perimeter 64 centimeters that yields the largest area is the rectangle with dimensions length equals 16 centimeters and width equals 16 centimeters. So after I found that the length has to be 16 centimeters to give me the biggest area, I found what the width would have to be by going back to that equation, which I believe was perimeter equals 2 times L plus 2 times W. And you can use that equation to figure out what the width has to be after you find the length. Okay, so that is the end of the material for section 4.3. Hopefully this is helpful. Some of these optimization problems I think students find difficult, so if you have difficulty when you're completing the homework, please send me an email and let me know. And I will have the last section, section 4.4, up sometime tomorrow for you to watch. So see you then.